Hey all, so this is Math 116, section 5.3. 5.3 is a bit of a beast. It's going to be exponential and log equations. And then along with that, we'll see application problems using both of those forms of solving equations. So quite a lot of content in this section. So starting off with exponential equations, what we're going to do when we see an exponential is we're going to log both sides. So logs find exponents, and then the inverse. When we have log equations, we're going to end up writing them in exponential form. So we're going to kind of be going back and forth with the logs and the exponentials. So anyhow, exponential equations, we're going to log both sides. We're going to bring the exponent down in front. Remember, we had that property from the last section that says we can do that. And then we're going to solve whatever pops out of that. And then you'll see what I mean once I do a few of these, to remember to let your calculator do most of the work. So let me get an example. Okay, so for this first one, our first step is to log both sides. So I'm going to go log, and I didn't leave myself enough room, log on this side also. And our second step is to bring the exponent down using that property from the last section. So 2x log 8 equals log of 743. And then this is 2 times x times log 8. And log 8 is just a number, as is this one. So what we're going to do is just divide all the stuff that isn't x. Like if this was just 2x over here, we would divide both sides by 2. So I'm just going to divide by both things. So 2 and then log 8. And 2 log 8. So that cancels, I have x equals this. And then you just have to put that in a calculator and then give your answer to 3 decimal places. When you type this, something that's really important on these problems is if you have more than one thing in your denominator, you absolutely need to type those parentheses right there. So let me show you what it would look like on this calculator. So we're going to have, this should be pretty good, log of 743, and it opened a parenthesis, so I'm going to close that parenthesis and then divide by, and here's where you have to open that parenthesis, and then 2 times log 8. So 2 and then times log 8. And then I'm closing the first parenthesis on the log and the second parenthesis on the denominator, and then hit enter. And then we're rounding to 3 decimals, so we're going to be looking in the 4th place, and that's going to round up the place next to it. So in this case, we'll come back to paper now. The calculator answer was x equals 1.58953, yada yada. So rounding to 3 places. So 3 places is right there. So that means we look to this one, the 4th place, to figure out what to do with this. And since this rounds up to 0, we'd have x equals 1.5 and then 90. So this becomes 0, but then that 1 has to come over here. And if you just think rounding 89 cents up to 90 cents, same idea. For this next one, same basic plan. I should probably have a step 1a on the sheet of steps, which is if the exponential part isn't isolated like it was in this case, isolate the exponential. So the first thing I'm going to do is divide both sides by p. And this seems like a strange thing to have that on both sides, but you'll see some of the applications we have for this later. It makes more sense. So I'm going to cancel those, and now I have it kind of to this form. So 0.27 equals 4 negative x. And then I'll log both sides, and so we'll go log, and bring the exponent down. So log of 0.27 equals negative x log 4. And then I'm trying to get x by itself, so I'm going to divide by the negative, which is, this is like a negative 1. So I'll divide by a negative and then log 4. And you see the negative will make positive, and then this cancels. And for this one, if you successfully get that in the calculator, and assuming I successfully got it in the calculator, I got 0.9 0.44 when I did it. Okay, so for number 3, I'm going to do the same thing where I isolate the exponential part first. So I'm going to divide both sides by 8,000. And that's, again, to make this as simple as I can, so when I log, I get to bring the exponent down front. If there's multiplying, I would have to do a bunch more work, and it would not be good. So definitely the best plan here. Throwing that in the calculator, I got 3.75 equals, and canceling that, e to the 0.4x. So the last two examples I used log base 10. I could have also used natural log, it wouldn't matter. On this one, I definitely want to use natural log because of that base e, and you'll see that makes it just a little bit easier in a second. So here we have ln of 3.75 equals 0.4x ln e. And this time I happen to write parentheses. I'm really bad about that. In general, I should probably have parentheses around that, although it's sort of implied. So over here, here's where we want to use natural log. ln e right there, which is what we'll get every time we log an e, just equals 1, because it's what power do I raise e to get e. So this is just a big fancy 1. So that makes this piece drop out, and then I just have to divide over the 0.4. And that gets me x by itself. So it's a little less to put in the calculator if you use ln with e. This one I think I'm going to copy on another piece of paper because it's going to take a little bit of room. Okay, so this one is totally not in a good form. The exponential is like wrapped up in a fraction. So the first thing I'm going to do is just clear the fraction. So I'm going to do this to both sides. And so that will knock that out, which just means I have that same exact factor over here. So then these cancel, and give me a second, I'm going to rewrite this and come back and then show the next step, but it will be a bunch of writing. Okay, so now I'm here and all I did was rewrite this kind of the other direction with equals to 70. So now I'm going to divide both sides by 50. And that's going to make this side be 1.4. And so then give me a second, I'll rewrite that. Okay, and then I'm going to subtract 1 on both sides. Lots of writing in this problem. So 7e negative 0.4x equals 0.4. And then I've almost got this piece by itself, so I'll divide the 7 over. And I think this didn't turn out to be a good number because I left it like that. So now we have e negative 0.4x equals that number. And so now I'm finally down to just the exponential, so I'll natural log both sides because of that e. And then I bring this down front. Oops. And then remember this piece is 1, and then so we'll just divide both sides by the negative 0.4. So that drops out. So now we have x equals natural log of whatever this decimal 0.4 divided by 0.7, but 0.4 divided by 7 is. So whatever that number is, and then divided by this. And what I got was x came out to about 7.155 to 3 decimals. Okay, these next 4 problems are the ones I would have you try in class, although I can't imagine I'd ever have time. So I'm going to go through these a little bit quicker because they're matched to the ones I just did. So for number 5, I'll log both sides. It's kind of our basic first step as long as the exponential is by itself. bring the exponent down front. That's kind of our second step. And then divide out whatever you need to divide out to get x ln. So we'll do 3 log 4 and 3 log 4. And then when I put that in the calculator, I get I get x equals 0.695. Hopefully I have some whiteout up there, so hopefully that's right. For this one, first thing I would do would be to divide the 10,000 because there's my exponential piece. So anything else going on around that, I want to get out of the way. So I'm going to divide this over. And then that gets me to here. So now that I have the exponential by itself, I will log both sides. And I could do log or natural log, it wouldn't matter. I'll just write log. Here, bring that down front. And then we're going to divide everything that isn't x over to the other side. So we'll do the 4 log 1.27. Same thing over here. And that cancels, that cancels. So now I have that x by itself, and if I throw that in a calculator successfully, let's see, I got 0.191 when I did it. Okay, so number 7. For this one, I would divide over that 1500. Again, trying to get the e part by itself. And then I think that came out to 6.6, but with repeating 6's forever. And so I'm just going to represent that way. And now it's an e, so I'm going to use natural logs. So natural log both sides. And so we have ln 6.6 bar. Bring this down front. Remember, ln e equals 1. So now we're just dividing over the 12 on both sides, so 0.12. And then when you put this in a calculator, have this on your calculator screen already. So in other words, actually, let me go ahead and show this. So we're going to go 10,000 divided by 1500, so that number's there. And then just use your answer button. So we'll go natural log, second function, answer, and it copies all those zeros for you. And then you just divide by 0.12. And then there's our answer. And that was x equals 15.809. Number 8, this one's a little bit different. So again, we need to get this e part by itself. And so first thing I'm going to do is I'm going to subtract over this 100. And that's going to get me negative 47 equals, that's gone now, negative 100 e to the negative 0.04x. And then I'll divide out the negative 100 on both sides, and that's going to get, again, that exponential piece by itself. So now this makes 0.47 equals e negative 0.04x. So we're back down to the exponential, so this is where we're going to log both sides again. So isolate the exponential, log both sides, bring the exponent down, and then solve. So here we have ln 0.47 equals negative 0.04 x, and then again ln e was 1. So I'll divide this over. and then x equals, I think, 18.876. Okay, so now we're on to part 2, which is going to be log equations. And with the log equations, we're going to do something with exponentials to solve those. So again, they're kind of the forwards and backwards of each other because of that inverse relationship. So we have kind of 2 forms of log equations we're going to see. We're going to see one kind where every term involves a log, and we're going to see another kind when there's logs in a number. And I'm starting with the logs in a number, so I'll go through these steps and then loop back here when I hit those problems. So if there are logs in a number, that would look something like this thing coming up. So we got a log and a plain number as opposed to another log over here. So the first thing we want to do is make sure it's written as a single log. And so we want to get to this form. And then once we're here, we're going to change to exponential form. And remember, that's that base to the answer makes the stuff inside. So it's base to this makes that. And this is our base, our exponent, and then what we're used to thinking of as the answer. Once we have it in that form, we can solve it. And so 2 things can happen there. It can be linear, in which case we'll just get x's to one side, numbers to the other. Or it could be quadratic, and then we'd write it in this form and probably factor and solve. The last thing about log equations is that you can do everything right and get a fake answer. And so you cannot take log of a negative number. If you play with it, you'll see it's impossible. Or if you think of the graph of a log, it looks like this, and you can't put negative x's in there. So if you end up with an answer that makes it do this, then that's extraneous and you have to toss that answer. So let me show you what all that looks like with some steps and with an actual problem. Okay, so solve the equation, give your answer 3 decimals. So this one is already a single log, so that gets me to step 2, where I'm going to change it into exponential form from the log form. So we're going to go 3 raised to the 4 makes the argument of the log. So 3 to the 4th equals 8x plus 9. And then this is just a little linear equation, so we can solve that. So 3 to the 4th is 81, and that equals 8x plus 9. I'll subtract the 9 on both sides. 72 equals 8x, and then dividing over the 8, x equals 9. If I put the 9 in, it doesn't come out negative, so everything's good. That's a legitimate answer. Number 10, so this one we do have to write it as a single log. So I'm going to change this to ln x over 5, because remember, if it's a minus, it's in the denominator, equals 7. So that was our step 1. Step 2 is change the equation to exponential form. So remember, with this one, there's that little invisible e here. So we're going to go e to the 7th makes that stuff. So e raised to the 7th makes x over 5. And then we're trying to get x by itself. So I will multiply both sides by 5. And then just throw that in a calculator. And when I did that, I got x to be 5483.166. Okay, this next one's a little interesting because we have kind of logs strewn about and numbers strewn about. So I'm going to add the 2 log x over to this side with the other log. So I'm going to write down the log 8x. And then when I add this, it'll be plus 2 log x. And then we subtract this 3 over at the same time. So that's going to be 21 minus 3. So we're going minus 3 on both sides. And that equals 18. So now what I can do is, since this is a plus, I can write it as a multiply. Actually, let me do one thing first. So remember, with this 2, that's going to be an exponent. And you could do this all in one step, but I just thought I should probably show it as a separate step. And so now I'll do the plus, and I'm going to write that as a multiply. So 8x times x squared would make 8x cubed equals 18. And so from there, let's see, we can go, this is a base 10. So remember, when there's nothing here, that's an invisible 10. So we'll put a little visible 10 there. And we're going to go 10 to the 8th makes that stuff. So that is going to be 10 raised to the 18th. Sorry, I think I just said 8th equals 8, and then x cubed. So with the 8, I think I will divide that over. I could do either, but I think I like how that looks better. So now this is gone. And then what I'm going to do is I'm going to cube root both sides, and that's because of this x cubed here. So in order to undo the cube root, I have to go cube, cube. So what that does is gives me 10 to the 6th, and cube root of 8 would be 2, and 10 to the 6th is 1,000,000 over 2, and so, oops, and this equals x, and so x is going to equal 500,000. You can also just put this to calculator and it will tell you it's 500,000. Number 12, so this is the one that is if every term involves a log. So this is one that's a little bit different, so you can see it went log, log, log. So what we're going to do is write both sides of the equation as a single log. So we put these together just like we did kind of over here. And then if it's linear, x is one side. So when we get to log equals log, then we can dump the logs. So that's kind of the deal with this. And then we'll just solve what comes out of that. And if it's linear, cool, then x is one side, numbers the other. And if it's quadratic, then we have to get it to 0 and solve. And again, we can have extraneous solutions. So let me show you what that would look like with an example. So for this one, we got a plus, so I'm going to go log x, and then plus means multiply, right? So x minus 5 equals log 2x plus 8. And since I have log of this stuff equals log of that stuff, that only works if this stuff equals that stuff. So what I can do is get rid of the logs and just set these equal. And I'll distribute the x. And then right here I can see that it's a quadratic, so that means I want to get everything equal to 0 so I can factor and solve it. So my next move will be to subtract over the 2x and the 8. Could have gone the other way, but much easier to factor with the positive leading term. So x squared minus 7x minus 8. And now that equals 0. So from there, I can factor, and x minus 8 and x plus 1 would multiply to negative 8, add to negative 7. And then x equals 8, x equals negative 1. But negative 1, if I put that back in here, I'm trying to take a log of a negative. Remember, this is what we cannot have, is that. So this one is extraneous. If I put the 8 in, 8 minus 5, this stays 3, so it's still positive. That one will be positive. So that is our only legitimate answer. Okay, number 13, 14, and 15, those are the ones that I would have you guys try. So again, I'll go through these a little bit quicker. So this I'm going to just write in exponential form because I already have a single log. So 4 squared makes 5x plus 6. This would be 16 equals 5x plus 6. Subtracting over, 10 equals 5x. Divide the 5. And x equals 2. Okay, this one I think is going to come out exactly the same as the one I just did. I suspect probably all the ones on the homework come out like this, but we'll see. So I'm going to add this over. And then I'm subtracting the 7, and notice I'm getting the exact same thing as last time, 25 minus 7, 18, and then bringing that up. And then from here, it's identical to number 11. And so I would just refer you back to number 11 to see the finish of that one. But it should come out to 500,000 again. And then number 15, so this one has multiple logs. So we'll do ln, we're going to write it as a single log, x plus 3, and then times x equals ln x plus 8. I should probably have it like that. So now ln of this equals ln of that. So I'll just set these two equal. I'll distribute as I go. So x times x would make x squared, and then 3x equals x plus 8. From there I'll get everything over to one side. So minus x minus 8 minus x minus 8. And that will get you x squared plus 2x minus 8 makes 0. And then we factor and check our solutions. So I need two numbers to multiply to negative 8 and add to be 2. So it sounds like x plus 4 and x minus 2. Be suspicious of the negative numbers. So negative 4, if I put it in there, right, makes negatives. So that one's no good. X equals 2. That keeps everything positive. So that one is our real solution. Okay, so then the last third is taking that math that we just learned in the first two thirds, and then doing it with application problems. So number 16 goes the purchasing power P in dollars of an annual amount A dollars after 2 years of 5% inflation decays according to the formula that. How long will it be before a pension of $90,000 per year has a purchasing power of $30,000 per year? So what this is about, let me try to get this in slightly more understandable English. So if you retire 1 year, and right now, it's $90,000 is what your income is going to be. But if you live another 20 years, that $90,000 is not going to, it's still $90,000, but it doesn't buy anywhere near as much as it did 20 years earlier. So that's what the purchasing power is. So they're saying that that's going to decay over time. So with that little bit of help, P is our purchasing power, A is the annual amount after 2 years. So this is our annual, this is going to be our purchasing power, and then T is going to be our time. So what I would do is I'd set up a little A, and you're going to see as we go into the next chapter, oh my gosh, setting up this list of what you know is huge. So A and P. So we know that 90,000 is our A. That's how much it's worth now. And this A is always going to kind of be an initial amount. And then P is going to be our purchasing power, so that's 30,000. And so we'll just put those in here. So 30,000 equals 90,000 e to the negative 0.5 t. So t is what we're trying to solve for. And so first thing I'll do, so it's an exponential, so I'm going to isolate the exponential. This is what we just did in the first part. And then this is going to give me 1/3, because you can see everything cancels. And I think I'm just going to call that 0.3 with a bar to write it a little bit easier. And that equals e negative 0.05 t. It's an e equation, so we're going to natural log both sides. And so now I have ln 0.3 equals, this comes down front. And then remember ln e is 1, so that piece drops out, and then I just divide this over. And then putting this in a calculator, that will get me t, and I got to 2 decimal places, 21.97 years. Okay, so this is part B of that same problem. I just brought over the formula to this page. So B goes, how much pension A, so what the amount of A would be needed so that the purchasing power P is $50,000 after 13 years. So how much would it have to be worth today so that in 13 years it's still 50 grand? So that means that we're solving for A, we know T, and we know P. So P is going to be our purchasing power, 50,000. A is what we're looking for, e to the negative 0.05, and then T is 13. So from here, this would just be some number. So I'm just going to divide this side by whatever that number is and not bother to turn it into a decimal. And so if you put this in a calculator, and if I were doing this on one of those little calculators, depending on, I might make this number first. And depending on your calculator, you may need, if it doesn't open a parenthesis there, you need to. Most of them do open a parenthesis there, but if not, do so. I'd probably just type all that in at once. Anyhow, if that works out, you should get, let's see, $95,777 to the nearest dollar. So number 17 goes, an initial amount of 100 grams of a radioactive isotope thorium-234 decays according to this model, where T is in years. How long before half of the initial amount has disintegrated? It doesn't actually, I don't know, disintegrated, but okay. This time is called the half-life of the isotope. Round your answer to 1 decimal place. So let me write this out a little bit bigger so I can point at it. So here's that formula, and we're trying to figure out how long until half of it has disintegrated. And so what that means is if we're starting with 100 grams of this, what we're going to have left is 50 grams. And what this formula does is for some time T, we put T in this formula, it will say how much is left. So we're going to try to figure out what T makes this side come out to 50. So and so again, half-life, we're looking for the time that only half of the element remains. So first thing we do, divide out the 100, as we do. And so that's going to leave me 0.5 equals this chunk of math. And then from here, I will natural log both sides, because we got base E again, and we're looking for an exponent. So that will give me ln 0.5 equals this part. And remember, that'd be down front of this ln E, but then ln E is 1. And so then next you just divide over that decimal, so I'll just kind of say dividing that over. And then I got T to be 24, 1 decimal place, 0.5 years. Okay, number 18. If the population of a certain county was 100,000 in 1998 and 110,333 in 2008, and if the formula of that applies to the growth of this county's population, estimate the population of the county in 2023. In the formula, they're saying P naught, that's that little 0 down there, is the initial population. And to round our value of H to 4 decimal places. Okay, so the first thing we kind of have to do is figure out this P naught deal. We know there's 100,000 people in 1998. So if I let this equal T equals 0, then this is the population at time 0. So I'm going to do that, and that will make that 100,000 P naught. And then I can do, so Y, the population later, equals P naught, the 100,000, E to the HT. So that's kind of what I'm working with. The next bit of information I have is then in 2008, this is the new population. So 2008, would be 10 years after 1998. So when t equals 10, p equals that 110333 number. So what that's going to let me do, notice we had, and actually I keep writing p here, let me write y, because this time it's the output instead of p naught. So what that does is I had three variables over here. I had t, h, and y. I now have a t and a y, so that means I can solve for h. So the y is going to be 110,333 equals the 100,000. E's E, H is what we're trying to work out, and I get this population 10 years after this time that I've declared to be 0. So that's a 10. Next we'll divide over the 100,000. And that's just giving me the same thing but with a decimal. So and then this is one that's base E, so we want to use natural log. And then we would bring this down front. And then hopefully I can just kind of point at it and say, so we'd have 10h would be there. So this will equal, just do this, 10h, and then divide both sides by 10. And then the directions say to round my value of h to 4 decimal places. So that would be, let's see where to go. Oh, interesting. So let me write this out. So it says to 4 decimal places, but it lied, and I thought there was something funky with this problem. So it's actually 4, I think this would be significant figures, not decimal places, because 4 decimal places is right there. So they want 4 actual numbers. And so then once you have that for your h, then you can figure out what they're actually asking for. So going back to this now is estimate the population of the county in 2023. So 2023 minus 1998. So 1, so that would be a 5, that makes that a 1 and a 1, so 25 years later. So now all I gotta do is say y will equal 100,000 E, H, so H is now this number, I'm just gonna call it big H is that, and then times 25. And then you just put all that in the calculator. And to the nearest whole number, I got this to equal 127,867. Okay, number 19. The total cost function for a product is given by this equation where x is the number of units produced. So we're saying that x is the units again, and the output is money. Find the total cost, so we're finding the total money, which means we're finding the output of producing 400 units around nearest cent. So that just means we're finding C of 400. So 650 ln of 400 plus 10, so 410 plus 1700. And then from there, it's just throwing that in the calculator. And to the nearest cent, I got $5,610.50. Part B is producing how many units. That means now we're solving for the x. Will give a total cost of 7,500. So we know the y. So this would be 7,500 equals a 650 ln. And this was x plus 10 plus 1,700. So now we're trying to get at this x, so I want to get everything I can away from the log. So I'm going to go minus 1,700, minus 1,700. And that'll give us 5,800 equals 65, or 650 ln x plus 10. And now the 650 isn't helpful, so we'll divide that over. And then this came out not a nice number, and so I just left that number on my calculator, but it looks like 8.923, and then it just keeps going forever. And that equals ln of, equals ln x plus 10. So then if you kind of picture this number over on this side, it might be more comfortable. So then what I did was e raised to that number equals that. So e, so writing in exponential form. And this would be something, I would just have this on my calculator and go e raised to second function, that answer. And that equals x plus 10. And then once I had that on the calculator, I'd go minus 10. And when I did that, I got x equals 7493 to the nearest unit. Okay, number 20, if $8,500 is invested at 12.2% compounded continuously, the future value S at any time t in years is given by this formula, rounding to 2 decimals. What is the amount after 18 months? Okay, so S is the future value, that's what we're looking for, how much we're going to have later. This is our equation. We'll figure out how these are formed in the next chapter, actually. So 8,500 e to the 0.122 in t, so we can't put 18 here. And that is because this is time in years. These financial formulas are always going to be in years unless otherwise stated, and that would be very odd for it not to be in years. So in years, 18 months equals 1.5 years. So that's what we got to plug in there. And then from there, it's just tossed into the calculator and it should come out to 10,206.92 to the nearest cent. And then part B is how long until the investment doubles. So if there is $8,500 in there to start, that means there's going to be $17,000 in there when it doubles. And this time we're looking for how long, so we're looking for time. So first thing I do is divide over the 8,500, and probably you can guess what's going to happen. It's just going to come out to 2. It's because it is doubling. So we could have kind of skipped that step and gone straight to a 2 here, but it makes more sense if you see why. And then same old, we natural log both sides. Exponent comes down front, so ln2 equals 0.112t, and then divide over the 112. And when I put that in the calculator, I got 5.68 years. 21, suppose the supply of X units of a product at price P per unit is given by P equals this. How many units would need to be supplied when the price is $55? So price was our output, units is our input. They're giving us price, so that means we're solving for how many units, we're solving for X. So just put the 55 in for P, and that equals 13 plus 6 ln 3x plus 1. And then isolate the log, so we'll take the 13 over. That will be 42 equals 6 ln 3x plus 1. It's not quite isolated yet, so I'll divide the 6. And that gets me 7 equals ln 3x plus 1. So remember, this has that invisible e. And if I put the 7 on this side, it looks a little better, to me at least. E to the 7th makes the stuff inside. So e to the 7th equals 3x plus 1. Now I can subtract the 1 over, and then just divide both sides by 3. And if you throw all that in a calculator, I got x to be to the nearest whole number, so 365 units. Okay, last problem, number 22. An investment service company experiences dramatic growth in the last 2 decades. The following models for the company's revenue are, and expenses or costs C, both in millions of dollars, are functions of years past 1990. So that means T equals 0 is going to be set at 1990. And then there's our revenue, there's our cost. use the model to predict the company's profit in 2028, round to nearest one decimal place. So you got to remember, we've seen it a few times now, that profit is going to equal, or P of X is going to equal revenue minus cost. And so we have these revenue and cost functions, so I can just put those in there, and that's going to give me P of X. So P of X is going to be revenue. It's the 21.4 E 0.131 T minus cost. And so that's, and so with these two, they're set up kind of perfectly. Normally that doesn't work out that way, but the problem's kind of designed to work. But if you look, all of this stuff, it's 21.4 of these minus 18.6 of these. So they're like terms. It's the same as if I had 21.4x minus 18.6x. I can just subtract them. And so when I do that, that'll give me my profit function. And that will be 2.8 of this. And then we're supposed to find the company's profits in 2028. So 2028 minus 1990. So 8, okay, ones, that is 38 years after 1990. So that makes, remember 1990 is t equals 0, so that makes this 38. So we'll just find P of 38. And then we throw all of this in the calculator, and if you do that, I got 406.5 million. Okay, so part B, how long before the profit found in part A, and that was 406.5 million, is predicted to double. So I times that by 2, so that means how long until it's predicted to be 813 million. So let's just double this. And then our profit equation from the last page, I just wrote that out here. So what we want to know is how long until, and this is years after 1990, so we're just doing it relative to that original equation because this is years after 1990. So we want to know the time for the output to be the 813. So we're just going to have 813 equals this side. And now we're solving for t. So the first thing I'll do is divide over this 2.8 and get that out of the way. And I think this makes one of those not nice numbers. So it's like 290.3, and then it just kind of keeps going from there. So ... equals e to the 0.131 t. And then we're solving for an exponent. So remember, logs find exponents. We're going to natural log both sides because of the base e. And we'll bring this down front. So now I have ln 290.3 ... equals 0.131 t. And then that would be times ln e, but again, that equals 1. And now we would just divide over the decimal. And then throw all that in the calculator. And so if you do, it ends up to the nearest whole numbers, the nearest year. I got t to be 43 years after 1990.